So I welcome you. Let's draw the waveforms for both rectification mode as well as inversion mode. So I will write here mode 3, that is u greater than 60 degrees. And this first of all we will take rectification mode. Rectification mode, and in this rectification mode we will assume let alpha be equal to alpha has to be greater than 30 degrees, so let alpha be 45 degrees and u be 75 degrees, because u is greater than 30 degrees. So we already know that 4-value conduction will last for, 4-value conduction intervals will be there for 120 minus u, alpha minus u, u minus alpha, that is 60 minus 45, that is 15 degrees. And 3-value conduction periods will be there for 120 minus u, that is 120 minus 75, that is 45 degree. So the 45 degree intervals. Now this is our waveform. So let us mark these. We will again start with the firing of value 3. So this is our, this is EBA, commutation voltage of value 3, followed by ECA, ECB, EAB, EAC, EBC, EBA again. So you already know how to mark these. Okay, so this is omega t equal to, this is the commutation voltage of value 3, original commutation voltage. Okay, which again we take as a reference, whereas actual commutation voltage is minus 1.5 EA for value 3, but we can take EBA also as a reference. So this is the zero crossing of EBA, so this is omega t equal to 0. Now what is alpha? You can see alpha is 45 degrees. Let us start measuring alpha 45 degrees from here. See, from here to here it is 30 degrees. From here to here it is 30 degrees. And from here to here it is another 30 degrees. So here to here it is 30 plus 30, 60. So this is here to here 30 plus 15. 15 is somewhere here. Half of this, 15. So this is total. This gives total alpha equal to 45 degrees. You can see 30 plus 15, 45 degrees. So which value will be fired at? Value 3. Now once you know the firing of value 3, then you can symmetrically find the firing instants of other values. Other values will be fired symmetrically after every 6 degree interval. So if this is here value 3 is fired, then symmetrically here value 4 will be fired. Then you can continue like that, like this. Value 5, value 6, value 1, value 2, value 3 again. Okay, we started with value 3, we ended with value 3. So then cycle repeats after value 3. So alpha is equal to 45 degrees. Now I have already drawn the converter power circuit diagram, and these are the firing instants. Here value 3 is fired, so we get 4-value conduction, 6123, and for 6123 load voltage VD is 0. I will write here 0. Load voltage is 0. Okay, and 123. 123. What is load voltage? When we have already drawn the table, we can quickly find from power circuit diagram. 1 and 3 are conducting, 2 is not. 1 and 3 is conducting, 5 is not conducting, and 5 means EC. So load voltage is minus 1.5 EC. Then again value 4 is fired, so there is again 4-value conduction, so load voltage is again 0. Then 2, 3, 4, 3-value conduction is there with 2, 3, 4 conduction. 2 and 4 in the bottom group are conducting. Which value is not conducting? 6. 6 is connected to EB. So your load voltage will be plus 1.5 EB. Then again value 5 is fired and it gives four value conduction, 2, 3, 4, 5, and we know that in every 4 value conduction period load voltage is 0. Then 4 value conduction is followed by 3 value conduction, 3, 4, 5. Now 3 and 5 in the upper group of values is conducting, value 1 is not conducting, and 1 is connected to EA. So our load voltage is minus 1.5 times EA. So once this is there, then value 6 is fired. This is 4 value conduction, again 0. And then you can take opposite of this. If this was 1.5 EC, this will be minus 1.5 EC. Okay. So again 0. This was 1.5 EB, this will be minus 1.5 EB, just opposite. And then again 0, and finally if this is minus 1.5 EA, here load voltage is plus 1.5 times EA. That's it. What about value voltage? During this period value 3 is conducting, so value voltage is 0. During next interval also value 3 is still conducting, 0, 0, 0, 0, 0, 0. So value 3 is conducting up to this. After this value 3 is off. Okay. And 4, 5, 6 are conducting. What is the commutation voltage of what is the voltage across value 3 when 4, 5, 6 are conducting? Just opposite of load voltage. If load voltage is minus 1.5 EC, it will be plus 1.5 EC. Then 0, this is minus 1.5 EB, value voltage will be plus 1.5 EB. Then value voltage is again 0. If load voltage is 1.5 EA, value voltage will be minus 1.5 EA. So we have completed our table. With this table, we can now go for drawing the waveforms. Now, again, this is EB, A equal to 0 here. If you take it down, it corresponds to this point. So, therefore, this has to be EB and this has to be EA. Okay. One of the students had previously asked me why this not EB and this not EA. It was a good question, relevant question. The answer to this question is that EB lags behind EA by 120 degrees. So, therefore, peak of EA will come first, and then after 120 degrees peak of EB will come first. After 120 degrees will come the peak of EB. So that's why this has to be EA, because it leads EB by 120 degrees, or EB lags EA by 120 degrees. So EA, this will be EA, this will be EB. So if this is EB, this is EC, and then this is EA. You already know, we have done it in the last class. So if this is EB plus EB, this will be minus EB. If this is plus EC, this will be minus EC on this side, and this will be minus EC on this side. If this is minus, if this is plus EA, this will be minus EA on this side, and this will be minus EA on this side. What is this? This is minus EB, this is plus EB. Okay. Now we already know if you multiply this minus EC by 1.5, you get minus 1.5 EC, and if you draw minus 1.5 EC on the same omega t axis, this axis, it will pass through this. You see, this is minus 1.5 EC. This is minus 1.5 EC. It's 0 crossing here. This is its 0 crossing. So you can come down. This is minus 1.5 EC. You can get it down. This is its 0 crossing. You can get it down to its 0 crossing. So this will have positive half cycle, and then you can draw the negative half cycle, but you don't need to draw the entire negative half cycle. So this is your minus 1.5 EC. Okay, what is next? Next is EB. So multiply it by 1.5, you will get plus 1.5 EB. Okay, plus 1.5 EB when drawn on the same omega t axis, it will pass through this. And what is the 0 crossing of 1.5 EB? This is 0 crossing of 1.5 EB. Take it up. So this is its 0 crossing. So this is plus 1.5 EB. You can take it down up to its 0 crossing. This plus 1.5 EB. Next is minus EA. So its 0 crossing is this. Okay. So this is minus 1. If this is minus 1.5 EA, so it will be like this. Minus 1.5. Okay, this is plus 1.5 EB. This is minus 1.5 EA, and then next is 1.5 EC, because this is EC, is 0 crossing is this. These are the zero crossings. Let us draw these zero crossings for phase 1.5 phase voltages. Okay, so this is EC. 1.5 EC will pass through this and it will go up to its zero crossing. 1.5 EC. Next is minus EB, and minus 1.5 EB will pass through this. See, this is minus 1.5 EB. Next is EA. 1.5 EA is this. 1.5 EA. Next is minus EC again, and this is minus 1.5 EC. So that's it. So what about these these crossover points? See, if this is minus 1.5 EC, its phase reversed voltage will be plus 1.5 EC. ये देखिए, they meet here. So if this is minus 1.5 EC, this will be plus 1.5 times EC. Fine. So you continue like this. Next is this. Let me first complete. Next is this. Next is this. Next is this. Next. And finally this. So this is plus 1.5 EC. This was minus 1.5 EC. This is plus 1.5 EC. Okay. This is plus 1.5 EB. This is obviously minus 1.5 EB. Right? Similarly, this is minus 1.5 EA. You can see this is minus 1.5 EA. So this will be plus 1.5 EA. Then this is plus 1.5 EC. You can see this is plus 1.5 EC. This will be minus 1.5 EC. Then this is minus 1.5 EB. This will be plus 1.5 EB. Then 1.5 EA. You can see this is 1.5 EA. This will be minus 1.5 EA. Then this is again minus 1.5 EC. You can see, and this is plus 1.5 EC. So we are now ready to draw the waveform. Let me use different color pen, say green color pen, for drawing this. This is alpha equal to 45 degrees. Okay. Before I draw this, we have taken EBA again as reference. But what is the actual commutation voltage of value 3? We already know it is not EBA. It is minus 1.5 EA. And why it is minus 1.5 EA? Interestingly, you can see this is minus 1.5 EA. And if you take this minus 1.5 EA down, it will come to this point. Okay. So therefore, with respect to minus 1.5 EA, which is actual commutation voltage of your value, what is the firing instant, or what is the delay angle? It is not 45 degrees. It is 45 minus 30. It is only 15 degrees. Here to here, it is only 15 degrees. But if you take EBA as reference, your alpha is 45 degrees, because this is 30 plus 15, 45 degrees. Why alpha cannot be less than 30 degrees here? You can see, because if alpha is less than 30 degrees, so for example, here you have taken alpha 45 degrees. If alpha would have been less than 30 degrees, somewhere here, commutation voltage, which is minus 1.5 EA, would have been negative across the value. So value would have been reverse biased. So even if you would try to fire the value, it would not go into conduction. So therefore, minimum delay angle is this 30 degrees. So that's why here we have taken alpha 45 degrees, which is more than 30 degrees. So with respect to actual commutation voltage, minus 1.5 EA, it is 15 degrees only. But with respect to EBA, it is 15 plus 30, 45 degrees, which I have shown here, 45 degrees. So this should be clear to you. Fine. Now let us go to this table with when value 3 is fired. You have 4 value conduction, 6, 1, 2, 3, and load voltage is 0 for 15 degrees. So value 3 is fired here. Value 3 is fired here, you can see. So for 15 degrees, so see, value 3 is fired here for 15 degrees. यहाँ से यहाँ तक आपका 15 degrees है. Load voltage is 0. So I will shade it. So load voltage is 0. Then 4 value conduction is followed by 3 value conduction, 1, 2, 3. And when 1, 2, 3 are conducting for 15 degrees, there is 4 value conduction. and load voltage is 0. And for next 45 degree, because total segment is 60 degrees, 60 minus 15 is 45. For 45 degrees, 3 value conduction is there, and load voltage is minus 1.5 EC. Why is minus 1.5 EC? Interestingly, you can see this is minus 1.5 EC, this. So it will jump and it will follow this minus 1.5 EC till next 45 degrees. Next 45 degrees means next firing instant. This is your next firing instant when 4 is fired. So it will follow this. Fine. So you shade this. This is load voltage. Then here 4 is fired, and you again have 4 value conduction, 1, 2, 3, 4. For 15 degrees, load voltage is again 0. So it will go up and load voltage will be 0 again for 15 degrees. Then for next 45 degrees, when 3 value conduction is there, it is plus 1.5 EB. Why it is plus 1.5 EB? You can see this is plus 1.5 EB. So it will jump and it will follow this plus 1.5 EB. Yeah, आपका plus 1.5 EB है till next instant of firing. And then you don't need to see the table. See, this is your 0 degree interval followed by this 1.5 phase voltage interval, then again 0 degree, then 1.5 times phase voltage. You follow this pattern and it will be again 0 degree followed by this phase voltage, 1.5 phase voltage interval. So you continue like this. You don't need to see the table now. So this completes your load voltage waveform. So I will mark it as right VD. VD means load voltage waveform. So this is your load voltage waveform, VD. Fine. So load voltage during 15 degree intervals is 0, and during 45 degree intervals it is either minus 1.5 times some phase voltage or plus 1.5 times phase voltage. So it is 0, minus 1.5 EC, then again 0, then plus 1.5 EB, then again 0, minus 1.5 EA, 0, 1.5 EC, 0, minus 1.5 EB, 0, plus 1.5 EA, and so on. So this is your load voltage waveform. At no instant, load voltage is line voltage segment. It is never line voltage segment. So you can see there is a drastic dip in the voltage. It is either 0 or 1 point or minus 1.5 times some phase voltage. So this causes a drastic loss of voltage. Okay. What about the value voltage? This was the load voltage waveform. What about voltage across value 3? This is value 3 voltage table. So 1, 2, 3, 4, 5, 6, 7. For 7 intervals, it is 0. So this is 1, 2, 3, 4, 5, 6, 7. So that means from this to this, value voltage is 0. I can shade it. And I can, although there will be some overlap, but doesn't matter. So this is my value voltage. I can write here V3, value voltage. Thereafter, when 4, 5, 6 valves are conducting, my value voltage is plus 1.5 EC for 45 degrees. What is 1.5 EC? You can see 1.5 EC is this. Here is 1.5 EC. This is 1.5 EC. Okay, so it will jump to this. Yeah, आपका 1.5 EC है. So it will go to this 1.5 EC. And it will follow this 1.5 EC for 45 degrees. That means up to this. Wait for a moment. It is plus 1.5 EC. 1 minute. So I'm sorry. This is 1.5 EC. Minus 1.5 EB minus plus 1.5 EA minus 1.5 EC. there was one mistake here. When 4, 5, 6 valves are conducting, the load voltage here it was minus 1.5 EC, so it has to be plus 1.5 EC, and valve voltage accordingly has to be minus 1.5 EC. So because of this, there was some problem here. So again, we'll see that 1, 2, 3, 4, 5, 6, 7. For 7 intervals, valve 3 is continuously conducting, so valve voltage is 0 for 7 intervals. 1, 2, 3, 4, 5, 6, 7. For 7 intervals, valve voltage is 0. And then valve voltage is minus 1.5 EC for 45 degrees. Why is minus 1.5 EC? You can see this is minus 1.5 EC. I have written here. I have labeled it as minus 1.5 EC. It goes up, up, up. So that means your valve voltage will now follow this, not this. So it will be minus 1.5 EC till next instant of firing. That is this instant. So it will follow this up to this. Okay. And then valve voltage is 0 for 15 degrees. So it will go down and it will follow the same curve as this. It will be 0 for 15 degrees. And then it is here it is plus 1.5 EB. Why is plus 1.5 EB, by the way? See, this is your plus 1.5 EB. It's already marked. It is this. This is 1.5 EB. So your valve voltage will jump down and it will follow till next instant of firing. Next instant of firing means this, when 2 is fired. So it will follow this till next instant of firing. So this is your valve voltage. Then for 15 degrees, it is again 0. So this is your 15 degrees. It coincides. It's again 0. And finally, it is minus 1.5 EA. Why is minus 1.5 EA? It's already labeled. This is your minus 1.5 EA. So for 45 degrees, it will follow this. It will come down and follow till next instant of firing. Next instant of firing means till 3 is fired. So it will follow this. And then valve 3 is fired here again, and for 7 intervals, valve 3 is again 0. Valve 3 voltage is again 0. So this is your valve voltage. So I hope it's clear. So this is the this green waveform is the load voltage waveform, and this red is the voltage across valve 3 valve voltage waveform for rectification mode of operation, assuming alpha 45 degrees and U 75 degrees. Let us quickly draw this waveform for inversion mode of operation. Okay, now we will draw the waveforms for inversion mode of operation. I have written already the mode 3, U greater than 60 degrees. You can see inversion mode of operation, and we have assumed alpha 150 degrees and U 75 degrees. So this is our power circuit diagram of 6-pulse 3-phase 6-pulse converter, and this is the table. I have reproduced that table. Valve 3 is fired here, so it gives 4 valve conduction, 6, 1, 2, 3. Load voltage is 0. Valve voltage is also 0. This 4 valve conduction is followed by 3 valve conduction. During this 3 valve conduction, 1, 2, 3 valves are conducting. Load voltage is minus 1.5 EC. Valve voltage is 0. And likewise, this is the same table which just few moments back I have drawn for rectification mode of operation. Same table is for inversion mode of operation. And then this is the waveform sheet, and these are voltages EBA, ECA, ECB, and so on. So omega t equal to 0. Alpha is here 150 degrees. So let's start measuring alpha 150 degrees. This is 30 plus 30 60 plus 30 90 plus 30 120 plus 30 150 degrees. So this is alpha equal to 150 degrees, and here we can see valve 3 is fired. So just show alpha equal to 150 degrees, valve 3 is fired. And symmetrically, after 60 degrees, valve 4 is fired here. After next 60 degrees, valve 5 is fired. Then 6, then valve 1, valve 2, valve 3 again, and so on. Now this is my minus EC. If I multiply it by 1.5, it becomes minus 1.5 EC. Its 0 crossing is here, that is this. So this is if I take this minus 1.5 EC up, this is minus 1.5 EC. If I take it up and plot it on the same omega t axis, it will pass through this crossover point. You already know. I can drop it down. It will pass through this 0. This is its positive zero, negative zero crossing. You can see this is minus 1.5 EC, and if you complete the cycle, this is its positive zero crossing. If you take it up, it coincides with this point. So you take this up, so it will pass through this point, and then that's it. So here I have drawn complete positive half cycle of this is minus 1.5 EC, complete positive half cycle and complete negative half cycle. Why do know it's omega t, negative zero crossing from here? See, this is your minus 1.5 EC. This is minus 1.5 EC waveform. This is its negative zero crossing. When you take it up, it coincides with this. And when you complete, this is its negative half cycle, and this is its positive going zero crossing. And when you take it up, it coincides with this. So you can drop it. This is positive half cycle of minus 1.5 EC, which passes through this crossover point, and this is negative half cycle of minus 1.5 EC, which passes through this crossover point, and this is the completion of cycle. And then your next voltage is, see, this is 1.5, this is EB, multiply it by 1.5, this is 1.5 EB, take it up, it will pass through this zero crossing, its zero crossing is this. If you continue like this, it will again, it will pass through this zero crossing. You don't need to do that. You take it down, 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 and it will pass through this. What we can do, you can do like this. You can take, see, this is 1.5 EB, and this is its positive half cycle, and this is its negative half cycle. So this is 1.5 EB. Yeah, आपका 1.5 EB है. And next will be minus EA. Minus 1.5 EA will pass through this crossover point. ये भी नीचे जाएगा, and it will finally, ultimately, it will pass through this. I don't need to draw complete positive and negative half cycle. See, I can use the symmetry. This is minus 1.5 EC. This is plus 1.5 EB. This will be minus 1.5 EA. So this is my minus 1.5 EA. What is my next? Next is EC. 1.5 EC. It will have positive half cycle here, and negative half cycle जब आप इसका complete negative half cycle draw करोगे, it will pass through this. So this is 1.5 EA, sorry, 1.5 EA. The minus 1.5, this is minus 1.5 EC. Okay, next is this is minus 1.5 EC. Next is 1.5 EB. Next is minus 1.5 EA. Next is plus 1.5 EC. Okay, so you can continue like this. ये actually यहाँ से आएगा, but I am not sure drawing complete. I am just using the symmetry. So this will be minus 1.5 EB. Next here, this will be plus 1.5 EB, and this will be minus 1.5 EA. So we can continue like this. इनके phase reversals कहाँ होंगे? That means if this is minus 1.5 EC, this is minus 1.5 EC, इसका phase reversal ऊपर होगा, pass through this. It will be, see, this is minus 1.5 EC. This will be plus 1.5 EC. Plus 1.5 EC. So similarly, you can continue like this. This will be next. Okay, let us first of all draw the load voltage waveform. See, when value 3 is fired, it gives 4 value conduction for 15 degrees, load voltage is 0. Where is value 3 fired? Value 3 is fired here. So it's fired here, that means value 3 आपका यहाँ fire होता है, that means for 15 degrees. 15 यहाँ से यहाँ तक 30 degree है, 15 degrees means यहाँ तक. Your load voltage is 0. This is load voltage VD. Your load voltage is 0. Okay? And then 4 value conduction is followed by 3 value conduction, 1, 2, 3. And this 1, 2, 3, and during this period for 45 degrees your load voltage is minus 1.5 EC, means it is minus 1.5 EC till next instant of firing. What is minus 1.5 EC? You have already drawn this. Yeah, आपकी minus 1.5 EC है. Just go down, it will follow this minus 1.5 EC till next instant of firing. Next instant of firing आपकी है when 4 is fired. तो ये यहाँ से यहाँ तक माइनस होगी। उसके बाद again there is 3 value conduction, 4 value conduction, 3 value conduction, then again 4 value conduction, 0 for 15 degrees. So it will go down for 15 degrees. यहाँ से यहाँ तक 30 है, इसका half आप ले लीजिए, that is 15 degree. It will be 0. Then what is load voltage? Load voltage is plus 1.5 EB. You can see it is plus 1.5 EB. Why it is plus 1.5 EB? You have already, this is your, okay, this was minus 1.5 EC. Next is plus 1.5 EB. I have already labeled it. This is plus 1.5 EB. So it will go down and it will follow this plus 1.5 EB. Till next instant of firing when 5 is fired. 5 यहाँ fire होता है. So it will be plus 1.5 EB. Right? And then for 15 degrees, it will be again 0. So go up, you don't need to see the table now. And go down, it will follow this curve, next curve, which is minus 1.5 EA. So till next instant of firing. And load voltage will be again for 15 degrees, it will be again 0. Then it will go down, it will be plus 1.5 EC for till next instant of firing. That means when this valve is fired. So it will be symmetrical, identical to previous segments. Then it is again 0 for 15 degrees. So go down, follow the same pattern. You don't need to see the table. Go down, follow the same pattern. Go down, follow the same pattern. So this is your load voltage waveform. You can see that it is for 15 degree intervals, it is 0. And for 45 degree intervals, it is minus 1.5 EC, plus 1.5 EB, minus 1.5 EA, plus 1.5 EC, minus 1.5 EB, and plus 1.5 EA, and then again. So this is your load voltage waveform. Let us quickly draw the voltage across value 3. See, value 3 is conducting for 7 consecutive intervals. 1, 2, 3, 4, 5, 6, 7. And during these periods, you can see 1, 2, 3, 4, 5, 6, 7. Load voltage is value voltage is 0. So value voltage, I can write here V3. It is 0 during first interval. During next interval also it is 0. During next interval 3, 4, 5, 6, 7. So up to this it is all throughout 0. So I can shade it. Value voltage is 0 up to 3. Thereafter your value voltage when 4, 5, 6 valves are conducted, it is minus 1.5 EC. Why is minus 1.5 EC? If you see this is your plus 1.5 EC. ये आपका minus 1.5 EC है. Minus, wait for a moment. This is minus 1.5 EC. So it will go up, follow this curve till next instant of firing. Till next instant of firing. So ये इसको follow करेगा. So it will be plus 1.5 EC. And then for 15 degrees, it is again 0. So it will go down, and for these 15 degrees, it will be 0. Load voltage during this period is also 0, you can see. And then it is plus 1.5 EB. What is your plus 1.5 EB? This is plus 1.5 EB. क्योंकि नीचे आपका है minus 1.5 EB. So this will be plus 1.5 EB. Okay. So it will go up and follow this till next instant of firing. ये आपका next instant of firing है. So ये इस pattern को follow करेगा. For next 15 degrees, it is 0. So it will go down, and for next 15 degrees, it will be 0. And finally, for 45 degrees, it's minus 1.5 EA. ये अगर आपका plus 1.5 EA है, या आपका minus 1.5 EA है. So it will go up, and it will follow this pattern. ये इसको follow करेगा. It will be symmetrical. You need to know only the first interval, 0 degree interval, and then this. और बाकी आप symmetrically follow कर सकते हैं. You don't even need to see the table. And then value 3 is fired here again for 7 intervals. It will be then 0. So this is your value voltage. So therefore, for inversion mode of operation, as expected, we know our load voltage should have been negative. So it is negative. Its average value is also negative. And value voltage is positive. Whereas for rectification mode, For rectification mode, positive voltage segments are greater than negative voltage segments. So average voltage is positive because positive voltage segments are larger than negative voltage segments. And if you see the value voltage, see this is negative, and for small period it is positive, then again negative. So average value voltage is negative. So therefore, for rectification mode of operation, average load voltage is positive, but average value voltage is negative. And reverse is case for inversion mode of operation. For inversion mode of operation, load voltage is negative, its average value is also negative, but this value voltage is positive for most of the time, and average value voltage is positive. So this completes our discussions and drawing of waveforms for mode 3, that is U greater than 60 degrees. For rectification mode of operation, we assumed alpha 45 degrees and U 75 degrees, and we have obtained these waveforms. Green is for load voltage waveform and red is for value voltage waveform. And for inversion mode of operation, we have assumed alpha 150 degrees, U again 75 degrees, and these are the waveforms. Green is again load voltage waveform and red indicates value voltage waveform, voltage across value 3. So I again advise you, please go through these waveforms, draw this table, analyze the converter. Once this table is ready, you draw the waveforms, practice it for different delay angles for both rectification as well as inversion modes of operation. Draw the load voltage waveform and also voltage waveform across any value. We can take value of your choice. Practice it again and again till you become perfect in drawing these waveforms. So with this, I will now try to derive the average output voltage of converter for mode 3, that is for U greater than 60 degrees. Now let us derive the mathematical expression for converter average output voltage for mode 3, that's U greater than 60 degrees. Average output voltage, average DC output voltage or average output voltage. We'll derive the mathematical expression. We know that average output voltage Vd is equal to 0 when 3 valves are conducting, that is from alpha to alpha plus U minus 60 degrees, and 4 valves are conducting. Because we know that 4 valves are conducting for how much time? Alpha plus U minus 60 degrees. 4 valves are conducting for U minus 60 degrees interval. So if you are finding your value 3, so it gives 4 value conduction 6, 1, 2, 3, and during 4 value conduction your load voltage is 0. From alpha to alpha plus U minus 60 degrees, load voltage is 0. And then this 4 value conduction will be followed by 3 value conduction, that is 1, 2, 3. When commutation between 6 and 2 is over, 6 is out, 2 is in, so it gives 3 value conduction 1, 2, 3. And 3 value conduction is there for 120 minus U degrees. And what is the load voltage when 1, 2, 3 valves are conducting? Few moments back we have drawn the equivalent circuit, and we have found that when 1, 2, 3 valves are conducting, our load voltage is minus 1.5 EC, or I can say minus 3 by 2 EC. Minus 3 by 2 means minus 1.5. So load voltage is minus 3 by 2 EC. That is from alpha plus U minus 60 degrees to alpha plus 60 degrees. See, because for 4 value conduction your load voltage is 0, and for 3 value conduction this is your load voltage. This is 4 value conduction, this is alpha to alpha plus U minus 60 degrees. For 4 value conduction load voltage is 0, and this is your 3 value conduction, and for 3 value conduction load voltage is minus 3 by 2 EC, which is shown like this. So this is alpha plus 60 degrees. So you fire your value 3 here at alpha. Here you fire value 3. And then for alpha plus U minus 60 degrees, there is 4 value conduction and load voltage is 0. And for rest of the period, your load voltage is minus 3 by 2 EC. This is minus 3 by 2 EC. And that completes this 60 degree interval. So in this 60 degree interval, for some time, that is alpha plus U minus 60 degrees, load voltage is 0. And for rest of the period, your load voltage is minus 3 by 2 EC. So therefore, our total time interval is from alpha to alpha plus 60 degrees. So therefore, for 3-valve conduction, 1, 2, 3, our load voltage is minus 3 by 2 EC from alpha plus U minus 60 degrees to alpha plus 60 degrees. This is the end of interval. So therefore, converter average output voltage. Converter average output voltage. If you find converter average output voltage, it will be like this: capital VD is equal to 1 by pi by 3, because the interval is 60 degree interval. All intervals are 60 degree intervals, times first 4-valve interval, 4-valve conduction intervals from alpha to alpha plus U minus 60 degrees, and during 4-valve conduction, load voltage is 0. So I will write 0 plus 4-valve conduction will be followed by 3-valve conduction, and 3-valve conduction is from alpha plus U minus 60 degrees to alpha plus 60 degrees. And during this 3-valve conduction, what is your load voltage? It is minus 3 by 2 EC d omega t. Okay, now let us try to simplify it. So this is equal to, I can take this 3 up, so this is 3 by pi times 0. I will not write. I will write integration alpha plus U minus 60 degrees to alpha plus 60 degrees minus 3 by 2. What is EC? EC we already know. We have got this EC from phasor diagram. We used this EC expression in one of the previous lectures also, when we were deriving the mathematical expression for converter average output voltage for mode 1, that is U less than 60 degrees. If you remember, this EC is EM sine of omega t minus 60 degrees, minus pi by 3, that is minus 60 degrees d omega t. Okay, so let us further simplify it. The further simplification gives VD is equal to average output voltage is equal. See, this is 3, this is also 3 on 9. I will take this EM also out. 9 EM by 2 also I will take out. 9 EM by 2 pi. What is inside is integration alpha plus U minus 60 degrees to alpha plus 60 degrees. So I will get minus sine of omega t minus 60. It is not omega t minus 60, it is omega t minus 90 degrees. So it is omega t minus 90 degrees d omega t. Just check it. If you remember, EC is equal to EM sine of omega t minus pi by 2. You can find it from the phasor diagram. We have already got it from the phasor diagram. So this is EM sine of omega t minus 90 degrees. That's what I have written here. So by mistake earlier I had written 60 degrees, but it is not 60, it is minus 90 degrees, minus pi by 2. Okay, anyway, so this is 9 EM by 2 pi. What is integration of sine? It is minus cosine. There is already minus there, so it is plus, minus and minus plus. Cosine of omega t minus 90 degrees, and the limits of integration are alpha plus U minus 60 degrees to alpha plus 60 degrees. Let us further simplify this. So this gives 9 EM by 2 pi times cos of omega t. You substitute alpha plus 60 degrees. So this is alpha plus 60 degrees minus 90 degrees. Okay, minus cos of omega t will be substituted by this alpha plus U minus 60 degrees and then minus 90 degrees. Okay, so this will be further equal to 9 EM by 2 pi. This is cos of alpha 60 minus 90 is 30 degrees. Alpha minus 30 degrees minus cos of alpha plus U minus 60 minus 90 is 150 degrees. And remember, cos of alpha plus U minus 150 degrees is equal to minus cos of alpha plus U plus 30 degrees. Cos of omega t minus 150 degrees is minus cos of omega t plus 30 degrees. You can use this trigonometric identity and you can substitute and further simplify your mathematical expression for converter average output voltage. So therefore converter average output voltage is 9 em by 2 pi times cos of alpha minus 30 degrees. So then minus cos of alpha plus u minus 150 degrees, that is minus cos of alpha plus u plus 30 degrees, minus and minus become plus, plus cos of alpha plus u plus 30 degrees. This is the final mathematical expression for converter average output voltage. I can also write it like this: Vd is equal to root 3 by 2 Vd naught times cos of alpha minus 30 degrees plus cos of alpha plus u plus 30 degrees. Where what is Vd naught? Vd naught is equal to 3 root 3 em by pi. See, if you substitute this Vd naught equal to 3 root 3 em by pi here, you will get same 9 em by 2 pi. So therefore finally this is our mathematical expression for converter average output voltage with 3 and 4 value conduction. The expression for average output voltage will not be same as for 2 and 3 value conduction, and it will not be same as that for 2 value conduction. Okay, for 2 value conduction, your mathematical expression for converter average output voltage is Vd is equal to 3 root 3 em by 2 pi cos alpha. Sorry, Vd equal to 3 root 3 em by pi cos alpha. For commutation overlap case, mode 1, that is u less than 60 degrees, in last lecture we derived the mathematical expression for converter average output voltage, and we have found that it is Vd naught by 2 cos alpha plus u. That is 3 root 3 em by 2 pi times cos alpha plus u. And for today's case, that is mode 3, u greater than 60 degrees, converter average output voltage gets modified to 9 em by 2 pi times cos alpha minus 30 degrees plus cos alpha plus u plus 30 degrees, or in terms of Vd naught, it is root 3 by 2 Vd naught times cos alpha minus 30 degrees plus cos alpha plus u plus 30 degrees. So we can also write it like this: Vd is equal to root 3 by 2 Vd naught times cos alpha dash plus cos delta dash, where this alpha plus u is delta. So where alpha dash is equal to alpha minus 30 degrees and delta dash is equal to delta plus 30 degrees. That is alpha plus u plus 30 degrees. Because alpha plus u we can take as delta. Okay. So for mode 1, if you remember, for mode 1, that is u less than 60 degrees, which we have derived in last class, average output voltage was Vd naught by 2 times cos alpha plus cos delta. That is cos alpha plus u. But here it gets modified to root 3 by 2 Vd naught cos alpha dash plus cos delta dash, where alpha dash is equal to alpha minus 30 degrees. So some very important findings are there. The finding is that average output voltage produced by the converter for mode 3, that is u greater than 60 degrees, is even less than that produced by same converter when it is operating in mode 1, that is u less than 60 degrees. It's because of the fact that alpha cannot be less than 30 degrees. We have already established that if you take EBA as reference, alpha cannot be less than 30 degrees. Alpha has to be greater than, because here if you substitute alpha less than 30 degrees, this will get a negative quantity. This term will be negative. So alpha has to be greater than 30 degrees. And second thing is that for 4 value conduction, your converter produces 0 voltage. So we can summarize that average output voltage drastically reduces on two accounts. What are those two accounts? What are the causes for drastic reduction in average output voltage? Number 1, alpha has to be greater than 30 degrees. Whereas this was not the restriction when we were analyzing the converter for u equal to 0 and for u less than 60 degrees, mode 1. There alpha could have been 10 degrees, 15 degrees, even less than 30 degrees. But here You can see in the equation also, and I have already explained it with the help of waveforms also some time back, that alpha has to be greater than 30 degrees. Since alpha has to be greater than 30 degrees, so that causes reduced average output voltage. And secondly, for 4 value conduction intervals, or conduction periods, converter output voltage is 0. And in 2 and 3 value conduction, you never found your output voltage was never becoming equal to 0. It was either equal to line voltage segment or minus 1.5 times some phase voltage or plus 1.5 times phase voltage. Here average output voltage is either minus 1.5 times phase voltage or plus 1.5 times phase voltage and 0. For 4 value conduction periods, it's always 0. So since it reduces to as low as 0 value for 4 value conduction intervals, this drastically reduces the converter average output voltage. So therefore, mode 3, that is U greater than 60 degrees, which is the worst case as far as commutation overlap is concerned, it results in drastic reduction in converter average output voltage, large loss of output voltage on 2 accounts. Number 1, alpha has to be greater than 30 degrees. Since alpha has to be greater than 30 degrees, so converter average output voltage will reduce, because as alpha increases, output voltage decreases. And secondly, for all 4 value conduction periods, converter gives zero output voltage. So that causes large loss in the voltage. So converter average output voltage sees a large reduction. So with this, I will end my today's lecture. Summarizing what we have seen, we have today analyzed converter. We have done the converter analysis with commutation overlap for worst case, that is mode 3, U greater than 60 degrees. And we have, drawn the waveforms, and from the waveforms we have derived the mathematical expression for converter average output voltage, which is given by this equation. And we have found that this converter, when operating in mode 3, produces it results in drastic reduction in the average output voltage of the converter. So with this, I will end my today's lecture, and I advise all of you to go through this lecture, analyze the converter, derive the mathematical expression for converter average output voltage, draw the waveforms itself for different delay angles, both for rectification mode and as well as inversion mode. So I will end my today's lecture here. Thank you very much.